In building a bridge, an engineer might be interested in the response of the bridge when weighed down by loads at the various points along the bridge. Imagine, for instance, a single beam with forces at n points along the beam. We'll keep track of those n forces with a force vector F with components F1 through Fn. And let's imagine that the beam is somewhat elastic, and so it'll bend due to the forces. And at each of those n points, there is a deflection of the beam from the horizontal. Those displacements will be recorded in a vector d with components d1 through dn. We're interested in the relationship between the force vector F and the displacement vector d. Now, if you've taken any physics, you might recall that in spring mass systems there is a law known as Hooke's law that says that the force on a spring is proportional to the displacement of the spring from its resting position. Here, similarly, there is a linear relationship between the vectors F and D. In fact, D equals a matrix A times F, where A is an n by n matrix known as the flexibility matrix. The matrix A reveals how a deflection at a particular point arises as a linear combination of the forces at each point. The entries of A can be determined by seeing how the bridge responds to the various forces applied to it. For instance, if we have forces applied at 3 points along the bridge, then the matrix A is a 3 by 3 matrix. The first column of A can be determined by applying 1 unit of force at the first point and no force at the other 2 points, so that the force vector is 1, 0, 0. Then by measuring the deflection of the bridge at the 3 points due to the force vector 1, 0, 0, we obtain A times 1, 0, 0, which is the first column of A. Similarly, the other columns of A can be obtained by applying a single force at the other 2 points. You can see then that this matrix A represents a linear transformation that changes the force vector to a deflection vector. The matrix A is often called the flexibility matrix because it tells me how much the bridge will bend when I subject it to some given forces. As an engineer, you might be interested in the inverse question. If I want the bridge to bend no more than a certain amount, what is the maximum force it could take at the various points? In other words, given a deflection vector, what force vector will produce it? Is there a matrix K such that F equals K times D? If there is, we want to call the matrix K the inverse of A, because multiplication by K undoes the transformation caused by multiplication by A. We can see from this example the importance of understanding when a linear transformation can be inverted and when its associated matrix has what's called an inverse. Let us further motivate the notion of the inverse of a matrix by returning to something we've studied already: how to solve a system of linear equations using Gaussian elimination, which involved row reductions to change the system to an equivalent, simpler system in reduced row echelon form. Such a system has exactly the same solutions as the original. In this lecture, we will look at a system of linear equations from a different point of view by looking at the system of equations as a matrix equation AX equals B. While Gaussian elimination remains the best way of solving a system of linear equations, looking at them as a matrix equation is useful for many theoretical reasons. It'll help us see the general nature of the set of solutions rather than solving a particular problem. We can also take advantage of the matrix structure of A in a way that row reductions don't. Recall that if A is an m by n matrix and X is a vector of unknown quantities x1 through xn, and B is an m-dimensional vector, then AX equals B is a system of n linear equations in n unknowns. Notice that the left side is matrix multiplication, and we've seen that the function t of x equals a times x that performs matrix multiplication is a linear transformation that takes x, a vector in Rn, to t of x, a vector in Rm. It is a linear transformation because A times x plus y equals ax plus ay, and A times cx equals c times ax. By viewing the left side of ax equals b as a linear transformation acting on the vector x, we can see that solving the matrix equation ax equals b basically amounts to trying to find a vector x which gets sent to the vector b under multiplication by a. For instance, let's look at this system of equations. 2x1 plus 7x2 equals 5, and x1 plus 4x2 equals 3. We can rewrite this system as a matrix equation ax equals b, where A is the 2 by 2 matrix 2, 7, 1, 4. The advantage to viewing it as a matrix equation is that it puts attention on the linear transformation that takes the unknown vector x to the known vector b. What is this transformation doing to the vector x? Before pondering that, let's imagine a simpler equation that we are more familiar with, like this one. 5x equals 3. What is 5 doing to the unknown quantity x? Well, it's multiplying it by 5. So if I wanted to isolate the x to solve for it, I would need to undo what 5 is doing to x. You could think of dividing by 5 as undoing multiplication by 5. But if we were to apply this idea to matrices, we would be in trouble because we don't have a notion of division there. Is there another way to undo multiplication by 5? If you think about it a moment, you'll realize you can undo multiplication by 5 by multiplying again by 1/5 on both sides. So then we get x equals 3 times 1/5, which is 3/5. That's the solution. We can try the same idea with matrix equations like ax equals b. Can we multiply both sides of ax equals b by the same matrix to get something of the form x equals something? Looking at our numerical example, we could multiply 5x equals 3 by the number 1/5 on both sides, and because 1/5 times 5 equals 1, and because multiplication is associative, the left side is 1/5 times 5x, which is the same as 1/5 times 5 multiplied first times x, which is just 1x, which is x. So the key to solving the numerical equation is to multiply both sides of the equation by the multiplicative inverse of 5, which means that number which, when multiplied by 5, produces a number 1. The multiplicative inverse of 5 is 1/5. So similarly, for our matrix equation, it would be really great if we had a multiplicative inverse, something which, when multiplied by A, gives the equivalent of 1 for matrices. What's the equivalent of 1 for matrices? Well, that would be a matrix for which multiplication by it leaves other matrices unchanged. And remember, the identity matrix has that property. When you multiply the identity by any matrix, it leaves a matrix unchanged. The identity matrix consists of ones along the main diagonal and zeros everywhere else, and it's usually notated by the letter capital I. We're thinking of the matrix being an n by n matrix A, so the identity matrix for A is the n by n identity matrix. We'll call the multiplicative inverse of A, when it exists, A inverse, and we'll write it as an A with a -1 exponent. This is just notation that mimics how we sometimes write the multiplicative inverse of real numbers. A inverse has the property that A inverse times A, as well as A times A inverse, equals the identity matrix. If we had such an inverse for A, then we could take the matrix equation AX equals B and multiply both sides on the left by A inverse. Notice that when you work with matrix equations in this way, you have to be really careful to do the same things to both sides, and since order matters for matrix multiplication, You have to be sure that when multiplying things on both sides that you're doing the multiplication either both on the left or both on the right. So when you multiply AX equals B by A inverse on the left, because matrix multiplication is associative, the A inverse times A becomes the identity matrix I. But then I times X is just X. So you get the equation X equals A inverse times B. And that is the desired solution. You could just multiply out A inverse times B and you'll have the solution. We've thus solved for the unknown vector X as long as A inverse exists. So let's make a definition. Call a square matrix invertible, or sometimes we say non-singular, if there exists a matrix A inverse such that A inverse times A and A times A inverse equals the identity matrix. Let's look at an example. Consider the matrix 2, 7, 1, 4. It does have an inverse, and that's 4 minus 7 minus 1, 2. You can check that if you multiply these two matrices together in either order, you're going to get the identity matrix 1, 0, 0, 1. You should try it now. This actually might be surprising, and you might be wondering, how did I find the inverse? And why is it that I can multiply these in either order and still get the identity? I'll tell you in a short while. But now, notice that if I know A inverse exists, our earlier arguments show that the solution to AX equals B must be X equals A inverse times B. Let's see what this means for the system of equations we started with, the matrix equation AX equals B, where the matrix A is 2, 7, 1, 4, and the vector B is 5, 3. The solution is obtained by multiplying both sides on the left by A inverse, which yields X equals A inverse times 5, 3, which equals minus 1, 1. Do you see it? We've solved for X. Now take a moment to check that X1 equals minus 1 and X2 equals 1 solves the original system. You can just plug the numbers in and check that it solves the system. So we see that if a matrix has an inverse, we can solve the system of equations AX equals B. Now that's great, but sadly, not every matrix is invertible. For instance, the 2 by 2 matrix, 1, 1, 1, 1, has no inverse. You will not find a 2 by 2 matrix that you can multiply by this matrix and get the identity matrix. One way to see this is to realize if it had an inverse, then by the reasoning we just did, this system of equations would have to have a solution, no matter what A and B are. But if A and B are different numbers, then this system cannot have a solution because the quantity x1 plus x2 cannot add to two different numbers at the same time. From this example, we learned two things. The first is that there are some matrices that are not invertible. So, whenever we see a statement involving A inverse, we must be careful to remember that the statement only holds when A has an inverse. A second is that invertibility of a matrix A implies that the matrix equation AX equals B always has a solution for any vector B, and it is unique. There is no other solution. This is because X must be A inverse times B. It can't be anything else. In particular, if B is a zero vector, the equation AX equals 0 has only the solution X equals A inverse times the zero vector, which is the zero vector. So we can state this observation in a theorem. If an n by n matrix A is invertible, then the matrix equation AX equals B has a unique solution for any B in Rn. And in particular, AX equals 0 has only the trivial solution X equals 0. Soon, we'll see even more conditions that are connected to a matrix being invertible. Now recall that the n by n identity matrix is a matrix with ones on the main diagonal and zeros everywhere else. To find an inverse for an n by n matrix A, we seek another matrix that we call A inverse, which when multiplied on the left or right by A produces the identity. The simplest case is finding inverses for 1 by 1 matrices. There, matrix multiplication for 1 by 1 matrices just corresponds to multiplication of real numbers. And to find an inverse is just reciprocation, since the 1 by 1 identity matrix is just a matrix with a single entry, 1. And the product of a number and its reciprocal is 1. So the inverse of the matrix with a single entry A is a matrix with a single entry, the reciprocal of A, as long as A isn't 0. So if A is 8, the inverse of the 1 by 1 matrix 8 is the 1 by 1 matrix 1/8. And you can check that 8 times 1/8 is 1. But if A is 0, the matrix is not invertible, because no number, when multiplied by 0, will produce a 1. For 2 by 2 matrices, the identity is the matrix 1, 0, 0, 1. Then, if the matrix A, B, C, D has an inverse, it will be the 2 by 2 matrix D minus B minus C, A, times the reciprocal of the quantity 1 over AD minus BC. Let's check that this is true. If we multiply the matrix A, B, C, D by the matrix D minus B minus C, A, you will get a 2 by 2 matrix with the quantity AD minus BC along the diagonals and 0 in the other two places. So multiplying the factor 1 over AD minus BC makes this the identity matrix. Let's try an example using the matrix 1, 2, 3, 4. According to the formula, if we set A equals 1, B equals 2, C equals 3, and D equals 4, we find AD minus BC equals minus 2. So this means that the inverse is 1 over minus 2 times the matrix with entries 4, minus 2, minus 3, 1. This just gives a 2 by 2 matrix with entries minus 2, 1, 3 halves, minus a half. You should check that if you multiply this matrix by the original matrix 1, 2, 3, 4, in either order, you'll get the identity matrix. Notice that the 2 by 2 inverse formula is not valid in the case AD minus BC equals 0, since you can't take the reciprocal of 0. But is there a different formula that will give an inverse in that case? As it turns out, no. When AD minus BC equals 0, the matrix ABCD has no inverse. I'll leave you to ponder why, but we'll return to this later. The quantity AD minus BC is called the determinant of the matrix ABCD, and it plays a special role in determining whether a matrix is invertible. Before we discuss how to find the inverse of an n by n matrix, let's address a question you might be wondering right now after seeing the 2 by 2 matrix inverse. Is there another 2 by 2 matrix that could also be an inverse for the matrix ABCD? Or is the inverse of a matrix unique? As it turns out, a matrix inverse, if it exists, must be unique. And this is true in general for any n by n matrix that's invertible. And we can prove this in a rather nice way. Let's prove the following theorem. If A is invertible, then there is only one matrix A inverse with the property that A inverse times A equals A times A inverse equals the identity I. Now, at first glance, this rather general statement may look hard to prove. After all, we're trying to show for any n by n matrix, the inverse, if it exists, is unique. It may look like we have to consider case-by-case possible inverses with lots of different entries to try to rule out other possibilities. But the beauty of the proof I'm about to show you is that you never actually have to refer to specific cases. All I have to do is appeal to the properties of an inverse. This underscores the importance of looking at properties of objects we construct in mathematics. So given a matrix A that has an inverse, call it A inverse, the way we will proceed is to assume that there is another inverse, call it J, with the property of being an inverse for the matrix A. Then we'll use the properties of being an inverse to argue that J really must be the same as A inverse, so that there is only one inverse if it exists at all. This method of showing uniqueness is a common practice in math, to assume that there are two things with the desired property and show that they really must be the same. Let's start the proof. We've assumed that A inverse is an inverse for A. Now let's assume that there is another matrix J with the property that it is also an inverse for A. This means that J times A and A times J are both the identity I. Now we will show by a chain of equalities that J must be A inverse. First, notice that J equals I times J, since I is the identity matrix. But now we can replace I by A inverse times A using the property of A inverse. So I times J equals A inverse times A times J. But by grouping the multiplication of A times J first, using associativity of multiplication, we can replace A times J with I, since J is an inverse for A. But then A inverse times A times J is just A inverse times I, which is A inverse. So from the chain of equalities, we see that J must be A inverse, which shows that any matrix that behaves as an inverse for A must be identical to A inverse. This ends our proof. Now, I hope you are as delighted by this proof as I am. We never had to consider a specific example of a matrix or consider any cases. We just appealed to the properties of an inverse to show that if an inverse exists, it must be unique. Now, while we're having fun doing uniqueness arguments, let's do an aside and ask a question we didn't ask when we first introduced identity matrices. Is the n by n identity matrix unique? In other words, how do we know that this matrix is the only matrix that, when you multiply it by another 3 by 3 matrix, leaves it unchanged? Again, we will prove this by a uniqueness argument. We'll show that if there is another matrix K that behaves like an identity, it must be the identity matrix. Here's how we'll state this as a theorem. If, for all n by n matrices A, we have A times K equals K times A equals A, then K must be the n by n identity matrix. And the proof is very simple. It's a one-line proof. In fact, if you blank, you might miss it. Here goes. Let I be the n by n identity, and let K be another matrix that behaves like an identity. Notice that K equals K times I because I is the identity matrix. But now K times I is just I because K has a property of being an identity. So together, these two equalities show that K equals I. And we're done. Again, it's a real delight that we never had to argue cases or consider what entries K might have. We just used the properties to show uniqueness of the identity matrix. This shows that abstraction and appealing to mathematical properties of objects can be really powerful. And while we're on the subject of properties, let's record a few properties of inverses. If you think of taking inverses as an operation on square matrices, you might wonder, what happens if you take the inverse of a matrix A? Well, as you might expect, you should get back the original matrix, which we state as a theorem. If A is invertible, then A inverse is invertible, and A inverse equals A. Why is this true? Well, it follows by looking at this statement and thinking about what it means. This statement is saying that A inverse is an inverse for A because multiplying them in either order gives the identity matrix. But then it is also saying that A is an inverse for A inverse because multiplying them in either order gives the identity matrix. But since inverses are unique, and A inverse inverse is also an inverse for A inverse, then A inverse inverse must be A. End of proof. How does the operation of taking inverse mesh with other matrix operations like addition or multiplication? For multiplication, you might think that the inverse of a product is a product of the inverses, but we have to be a little careful here. First, remember that not every two matrices can be multiplied. The dimensions may not work out, but since invertible matrices are square, the product makes sense for matrices of the same dimensions. Second, the order of matrix multiplication matters. So if two n by n matrices A and B are invertible, then AB is invertible, and its inverse is B inverse times A inverse. We can state that as a theorem. Note that the order of B inverse and A inverse is backwards from what you might originally expect. You can see why and also check this result just by multiplying out AB times B inverse A inverse to see if you get the identity matrix, like so. By associativity of matrix multiplication, we can multiply together the B times B inverse first and replace it with the identity I. Then A times I times A inverse is just A times A inverse, which is I as desired. You should try the other order too, multiplying B inverse A inverse times AB to verify that you'll also get I. You can also try an example with actual numbers to see that this formula holds. But the point of doing a general proof is that you can see that this will hold from the properties alone rather than because of any specific numbers in the matrices. What about how addition meshes with taking inverses? Well, we have to be even more careful in this case. The statement that the inverse of a sum is the sum of the inverses is definitely not true. It's not even true for 1 by 1 matrices, which are just real numbers. For instance, the reciprocal of a sum is not the sum of the reciprocals. 2 plus 4 is 6, but 1/2 plus 1/4 is not 1/6. So don't even go there. Let's return now to the problem we started our lecture with. We were considering a deflection vector d caused by a force vector F, representing forces acting on a beam at n points. Thus d and F are n-dimensional vectors. And the relationship is linear, meaning d equals A times F for some n by n matrix A. And to find A, we can figure out how the beam responds to various forces. The question for an engineer is now, given a set of deflections, what force vector will produce it? This is the inverse question. Is there a matrix K such that F equals K times D? In engineering language, the matrix K is called the stiffness matrix because it tells me what force is required to produce a set of deflections. Let's see what the relationship must be between K and A. Well, if I substitute the equation D equals AF into the equation F equals KD, I see the matrix relationship F equals K times A times F. And if I substitute the equation F equals KD into the equation D equals AF, I see another matrix relationship, D equals A times K times D. These observations suggest that KA and AK should be the identity matrix. In other words, they suggest that the stiffness matrix K is the inverse of the flexibility matrix A. So finding an inverse in this context has a concrete physical meaning. In the next lecture, we shall return to the question of how to find an n by n inverse and why invertibility is such an important idea.